Okay, polar coordinates. The way you're used to specifying points in the plane by giving an x coordinate for how far over it is and a y coordinate for how far up it is, that's rectangular coordinates. That would be like if you asked me where my house was in the city and I told you to go 4 blocks east and 3 blocks north. If we were out in the country and there weren't any blocks or streets or buildings, I might tell you where something is by pointing you in a specific direction and telling you how far to go. I might say, it's 500 yards that way. And when you do that, when you specify where a point is by giving a distance and a direction relative to some central fixed point, you're using polar coordinates. So I could say this point is, you start at the origin or the pole and you go 5 units at an angle of about 37 degrees. You end up getting the same place as if you just went 4 spaces across and 3 spaces up, but it's a different way of specifying where that is. So every point can be addressed either with the x and the y, the rectangular coordinates, or with the r and the theta, the polar coordinates. So polar coordinates work by, you have a fixed specified point called the pole. It's really the same as the origin 0, 0 in rectangular coordinates, but for polar coordinates, we call it the pole. And then for any point in the plane, we can specify exactly where it is by giving numbers for r and theta. The r represents the distance from the pole, and the theta represents the direction. So face that angle and take that many steps, and you'll get to that point. Now, to convert back and forth between polar and rectangular coordinates, well, notice the trigonometry involved. For this point here, the x coordinate over the r would be the cosine of theta, and the y coordinate over r would be the sine of theta, and therefore x would equal r cosine theta and y would equal r sine theta, and that gives you formulas that let you convert from polar, r theta, to rectangular, x, y. Those are very straightforward. You just plug in the numbers and that gives you the x and the y. If you're converting the other way, it's a little bit more complicated. But we've already talked about those complications back in section 6.5 when we were talking about converting between standard form and trigonometric form of complex numbers. Going from the standard form, like 4 plus 3i, to the trigonometric form, like 5 times cosine of 0.6435 plus I times the sine of 0.6435. That's pretty much exactly the same as converting between the rectangular coordinates of a point and the polar coordinates of that point. So if you remember how to do that from section 6.5, it's really the same thing that we're doing now. So if you remember the calculator function from section 6.5, you can use that, or there's also another calculator function you can use, another method that works. So, well, different models of calculator have different ways of doing this, but on something like a TI-84, you can get to the angle menu by pushing second and then the button that says angle above it. and that gets you to a menu that looks like this. And 4 of the things on this menu are rectangular to polar R, rectangular to polar theta, polar to rectangular X, and polar to rectangular Y. So this first one, number 5 on the list, is what you could use to convert from rectangular coordinates to get the R of the polar coordinates. Number 6 you could use to convert from X, Y to the theta of polar coordinates. So in the example we were just looking at, where the rectangular coordinates were 4 for X and 3 for Y, if I want to convert them to polar coordinates the way I was just talking about, I'd go to the angle menu, I'd select number 5, rectangular to polar R, and I'd type in 4, 3, the X and Y coordinates of my point in rectangular coordinates. And what comes up is 5. So the R of the polar coordinates is 5. And then if I go back to the angle menu and select 6, and again put in 4, 3, what comes up is 0.6435 approximately. Now, right now I have my calculator in radians mode. So that gave me theta in radians. If I'd rather have theta in degrees, I can just go to degree mode and then put in that same thing. And in degrees, it's approximately 36.87 degrees. So when you're doing polar coordinates, the theta could be in radians or it could be in degrees. So let's do some practice. First, the easy way is going from polar to rectangular. So for each point listed here in polar coordinates, let's see where it is in the plane, and let's see what the rectangular coordinates of that point would be. Now, 3 pi over 2 means if you go at an angle of pi over 2, that would be straight up, same as 90 degrees. And 3 would mean you go 3 spaces that way, and that would take you right there. The rectangular coordinates, well, x would be 3 times the cosine of pi over 2, which is 0. And y would be 3 times the sine of pi over 2, which would be 3 times 1, or just 3. So that is the point 0, 3. Okay, let's try the point 2 pi over 6. The angle or direction pi over 6 would be this way. It would be equivalent to 30 degrees. And r is 2, so we go 2 spaces away from the pole in that direction. That would be this point right here. The x coordinate would be 2 times the cosine of pi over 6. That's 2 times square root of 3 over 2. So just square root of 3. And the y coordinate is r times the sine of pi over 6. That's 2 times 1/2, or just 1. So this is the point in rectangular coordinates that's over square root of 3, approximately 1.73, and up 1. Now, what about the point 4, 7 pi over 6? 7 pi over 6 is this direction. 6 pi over 6, or pi, would be here. So 7 pi over 6 is past that. 4 would just mean we go 4 spaces out, so right here. And if we convert to rectangular coordinates, I'm going to predict that the x and the y are both going to come out negative, because that does give us a point down here in the third quadrant. And if we actually do 4 times the cosine of 7 pi over 6 and 4 times the sine of pi over 6, 7 pi over 6, we get negative 2 root 3 for x and negative 2 for y. Okay, what about the point where r is 0 and theta is 13 pi over 91? So we're going 0 spaces away from the pole in that direction, And actually, the direction doesn't matter. If we're going 0 spaces away from the pole, we're staying just right there at the pole. The x-coordinate would be 0 times whatever that is, and the y-coordinate would be 0 times the sine of whatever that is. They would both be 0. So notice how when r is 0, you're right there at the pole, and it doesn't matter what theta is. Okay, now, next one, r is 5 and theta is negative pi over 4. So negative pi over 4 would be down like this way. It would be pi over 4 or 45 degrees in the negative direction. And 5 would be 5 spaces out away from the pole. And the cosine of negative pi over 4 would be square root of 2 over 2. The sine would be negative square root of 2 over 2. So the x and y coordinates of that point would be 5 root 2 over 2 and negative 5 root 2 over 2. Or approximately 3.54 and negative 3.54 in decimal. The point negative 3 pi over 10. Now this is the first time we've talked about what happens when r is negative. That is allowed, and what that means is if you face in the direction pi over 10, which is approximately this way, you're facing this way, but you take 3 steps backward, you end up here. So if we work it out by taking negative 3 times the cosine of pi over 10, that's approximately negative 2.85. And negative 3 times the sine of pi over 10, that's approximately negative 0.93. So we get down here in quadrant 3. An angle of pi over 10 is in quadrant 1, but when r is negative, we're facing that direction but taking 3 steps backwards, which ends us up in quadrant 3. So r can be negative, and when you have a negative r, that's just like having a positive r in the opposite direction. Finally, what about 1.57 pi? Well, where is 7 pi? Here's 1 pi. Here's 2 pi. That takes you all the way around the circle. 3 pi, 4 pi, 5 pi, 6 pi, 7 pi. So 7 pi is the same as just 1 pi, or 180 degrees. It's straight out along the negative x-axis. And if we go in that direction for a distance of 1.5 units away from the pole, that puts us right there. The point whose coordinates are negative 1.50. Now notice the same point can have more than one set of polar coordinates. You can take any angle and add or subtract 2 pi, or 360 degrees, and it's essentially the same angle, so it represents the same point in polar coordinates. And we talked about what happens when you have a negative r. Having a negative r is the same as having a positive r in the opposite direction. So making r negative while you're adding or subtracting pi, or 180 degrees, you end up with the same point. And as we've seen, if your r is 0, it doesn't matter what theta is, you're right there at the pole. So the pole has multiple possible polar coordinates that all start with 0 but have all different thetas. Okay, I'm going to end this part of the video here, and we'll come back in part 2 and do some conversions the other direction.